Hey, what's going on guys, GameOS here. In this video I'd like to demonstrate the game of Sokoban I've developed, and it's a boot sector game. However, first I'll demonstrate how this works under GameOS, the operating system I've developed for running boot sector games, and also here we can edit the data, like to customize the color scheme, for instance. I'll demonstrate that as well. And then we'll have a look how it works in an emulator separately, like just as the bare boot sector game. Then we'll have a look at the source code, and at the end we'll see how this works in real hardware. So if you're interested, buckle up and we begin. So the very first thing to demonstrate is just the bare game. So Sokoban, nothing special, but it wasn't really that trivial to fit this entire stuff into 512 bytes, to be honest guys. So yeah, this was a real challenge. So here I won, and now I can demonstrate. So I can push the box into the wall, which wasn't that trivial initially. I can push the box off, like through another box, and also we have this highlighting for boxes if we put the box onto the destination square. So all of this logic takes really lots, really a lot of bytes, and is kind of like the reason of doing this is actually to show how lots of things can be packed really tightly into a single app. Well, okay, so let's play around with customizing the color scheme. And before we're going to be customizing the color scheme of Sokoban itself, let me just customize the operating system theme in general. So if we go to the editor, okay, nothing here, so I just need to load the game first. So this is prog1, so let's go back to editor. Yeah, and here is the source code. Well, to be exact, this is not exactly the source code, but just the opcodes, the binary format. And down below, I'm sorry I don't have a mouse pointer here, but in the line where address of 06C0 in the center, there is a byte equal to 10, which is responsible for the wall color and wall kind of like wall character. Okay. So if I simply say 06C B, right, and I want to say, so I just changed B1 to B2 to get a bit different, character, and the color is going to be just reference in my notes. Hold on a sec. E1, right? Yeah, the color is going to be E1. So if we run the prog1 again, okay, nothing happens. That's because we need to save it first. So save and prog1. Yeah, and this is how it originally looked like. Unfortunately, on the real hardware, it doesn't work. It's just blinking because only 8 colors are allowed for background, and I was using E, which exceeds the 8 colors. It goes like to 16 colors, and that's the reason why on the real hardware it actually blinks. So even though I like how this theme looks like, so this was the original design, but unfortunately I needed to drop back to somewhat different. But anyway, so the reason why something strange happens on the screen is because it's a really tight program, and it just clears the part of the screen. And just to show you this a bit more, like how they should look like, there's going to be like this. If I run prog1 again, now this is how it's intended to be, basically, right? Now notice that you see, like, I can't move. So we have a box collision, so box doesn't go through another box. So also box doesn't go to the wall, which was really challenging to implement. Yeah, and yeah, this is how we go. And I just lost the game. Okay, doesn't matter. So let's play around with customization a little bit more, and if we just drop back to the editor. So well, for instance, we can try to change the box color. Let me just figure out the proper address for that. Yeah, here it is. So 06CA should be the box color. And let's try to make it, just finding this on screen, C06, yeah, it was 06. So let's make it, for instance, red, 04, right? And save, let's save it to prog2 now. Okay, and I just want to run prog2. No, I didn't save anything. I just run prog1. Sorry, I wanted prog2. Yeah, and here we have a version with red kind of like boxes, which is quite pretty awesome, right? A part of changing the color, we can obviously also change the character. We did this when we changed the wall character, but you probably didn't notice this. So let's change, for instance, let's change the destination target. So the address is 06CD, and the destination target, let's make it hearts. Okay, so save, and let's make it prog free, and here we have the hearts. Okay, however, it doesn't become green anymore because the logic of the source code relies on exactly the character we had previously, not this heart. So it just doesn't recognize. Hence, it kind of like has been a little bit broken. But anyway, and finally, we can use another different version of a smiley for the player. So instead of this transparent, we can add a bit of a solidity to it. So let's go and do it. So edit and 06CF, and let's make smiley like this. So it's gonna be a little bit fat now, just like me. Okay, and prog4, and yeah, now we have a fat smiley. All right, so this is it. All right, well, I could have changed the byte to compare with, to bring back the green lights again, but it takes ages to calculate the proper offset. So just hope you trust me, guys, that this is about to be working. So yeah, now let's just clear screen. Let's go back to initial theme, and let's have a look at different versions that we've created. So here is the original one again. All right, and yeah, and I lost the game. Okay, here is the second version that we've just created with the red boxes. All right, okay. Why am I pushing this box all of the time? Yeah, just losing for nothing. Yeah. All right. Yeah, it's easy to lose, but anyway, prog free. So another one like this. So maybe I win this time. Okay, like this. Yeah, now I'm gonna be winning. Just mispressed the button. Okay, maybe I just try to win the very last one. So prog4. No, let's go prog4. Final try, and be careful. All right. And here we go. So they complete the level. Okay, guys, so this is it regarding the demonstration under the GameOS. Now let's have a look at the source code. There are two versions of the source code, and I'll demonstrate how this works on different emulators, on QEMU and on the online emulator as well, where you can easily test this. And yeah, and then we'll talk about the source code. Okay, so I have two versions. So the first one is, I call it Sokoban OS. So it's a completely bootable version, and another one is Sokoban for GameOS. SokobanOS for GameOS. So the one that we've been working with just right a moment ago. So what's the difference? What's the core difference between them? So here, over the way, just label is a bit wrong here. Okay, so here we do initialize the data segment, because otherwise the offset being defined by the NASM won't hook up the variables properly. We have the variables down below here. All right, so one of the extra things to do in the bootable version, we need to initialize this data segment, okay? And also in the bootable version, we don't need to go back to shell, to go back to GameOS shell, right? While in the version for GameOS, we actually need to do this, and here is the jump. By the way, I just forgot to comment this. So here we want to jump back to GameOS shell, right? We don't initialize the data segment, and also there is a difference down below in the file. So here we have a pattern to formulate the entire floppy image. So just make it a little bit easier to see. So here we have a pattern to match like the floppy image, even though I run it on the real hardware. I run it using the USB flash drive, but anyway. And we need this absolutely essential boot signature, BIOS boot signature, right? So we don't have this in the GameOS version, because those 2 bits are taken by this far jumps in order to encode this address. That's exactly the number of bits that is needed to make sure it's going to be working. Okay, so yeah, now let's just run this in the emulator. So I save, and then I'll show you my pain, guys, like why it was so tough. So before we actually go to the very brief explanation of how the source code works. So yeah, let's compile and run this. So nasm-f bin sokobanos.asm -o sokobanos, and if it compiles, if it assembles, I want to say QEMU. I'm using QEMU emulator, system i386, and Sokobanos, and here we go. So this is how it looks in the emulator. Well, on the real hardware, it doesn't print these messages, it just goes on a blank screen. So yeah, this is how it looks. Yeah, it's the previous session I've been recording in a full screen. Yeah, I just lost the game, but anyways, I hope it's clear. But here we can't press escape, we can't go anywhere. This is just a bootable version, so that's the reason like why this is called, why does it contain OS in its name, right? But also, if you want to try this, you don't even need NASM or a QEMU to run this stuff. You can just use the browser, and there is a very nice online emulator. So copy.ch/v86, there would be a link in the description below this video. So here you can choose the hard disk drive image. Then you need to download the binary image. So I will provide this. So currently it's just called like Sokoban. I will provide this sokobanos.img file. So that would be really self-explanatory. But anyway, we need this binary file with a floppy drive bytes padding and the boot signature. So this is the file, and then just our emulation, and we're gonna see exactly the same thing. However, the colors in you see, like the colors in the browser are slightly different. The smiley is round, which is cool, but the game logic is still the same. So we can still move the boxes, and well, it looks quite pretty nice as well. Well, it's a bit too dark, but we can always change the color scheme if needed. So that's kind of pretty much all about it. Okay, now let's get back to the source code. And now, guys, just to give you an idea, so of how painful this was. So this is one of the in-between versions of the source code. And just to give you an idea, for those of you who has been developing boot sector games at least once in the life, you will definitely understand me. So I just want to assemble different files. So this one is called Sokoban overflow, and here we go. And can you believe this, guys? 81 bytes negative. So we have 81 bytes overflow. And can you believe that I did shave all of this 81 byte and even more. Eventually, I have shaved even more bytes. So the version I had within the last few days, so I needed to just let's say box would now hit the would now be just to give you an idea what I was doing. So if I just command this logic to box and wall collision, right? So if I just get rid of this box and wall collision, then it would be, then it would fit. And the instructions here are very expensive, so I'm using the variables. Later on, let's say I've replaced the map, which is the variable, by SI. So I've pointed SI to the map, and that really allowed to save lots of bytes. Also, I've refactored the code eventually, so the eventual version has a very detailed commentaries. So I'll quickly walk through that as well. Okay. So let me just get rid of box and wall collision, just to give you an idea what I was feeling actually. Okay, when it was so tough that I couldn't actually fit this into 512 bytes for quite a bit of time. This was really painful. So let's have a look if this now runs. We still have -26. Yeah. So still okay. Let's get rid of something else. Maybe, I don't know, up and down. Clear box. Yeah, let's get rid of box and box collision for up and down, for instance. Yeah, and this time there should be enough space. I just want to give you 3 more bytes. Oh my god! So this is really huge, guys. This is really huge currently. Move left, box left. Yeah, let's shave a bit more. Yeah, -1. Okay, what else? Oh man, what else to shave here? Some push or pop. Yeah, this one, for instance. Okay, now finally works. But here is the problem. So you see, like some crazy things going on. So we go down, that just doesn't work properly. We go up, we can move the box, but it just it goes to nowhere when it hits the wall, and box overlaps the box, which is very horrible. Okay, and the same for left and right. So this was very disappointing, and you know, like just to give you an idea how I felt when I initially managed to fit all of this logic into the proper into this 512 bytes. This was really cool. So I had an options like to have normal collision on one side but no collisions to the other. So let me just show you this. So for instance, let's get rid of all of the collisions here. So this command source code was annoying me for within the last few days. And yeah, this was really not that great thing, not the greatest thing ever. So yeah, just so literally what I had collisions only to one direction instead of 3 directions. So I could only make collisions into one direction that works properly. That was about it. And I'm just trying to recreate this from scratch. Really hope. Yeah. So yeah, now you see, like box doesn't hit the wall, like doesn't walk through the wall, and if I manage to, yeah, it's a bit challenging to do, but yeah. So here you see, like box is not hitting the box. Okay, so just I can't push the box there, right? So I can't push, I can't move here, I can't. Yeah, but now it goes to the wall, now it goes to the box, but only to the one side. However, it didn't work for the rest of the sites. You see, like it was complete nonsense there. So just to give you an idea how tough was it, and then when eventually I came up with this version that actually allows to do all of this stuff, to have all the collisions up, down, left, right as well. So let me just demonstrate the left to right collisions. So yeah, let's make it like so. Collision left, collision right, up. Okay, so not hitting box and wall collision, all the collisions. I was so happy, guys. I can't even even explain, express enough. I can't express enough how happy I was when this kind of worked. So this was the very first boot sector game I've developed in my life. And well, yeah, let's quickly walk through the source code. I'm not going to be covering the entire thing, just the very general ideas on the design. So here is how it works. So eventually we have kind of like 4 boards. So 4 boxes, 4 walls, 4 destination squares, so the places where to push the boxes, and for a player, so only single bit. And now the way how it is encoded, so the single word holds a single byte holds the entire row, but I group them by words. So let's say we have 2 kind of like 2 bulks, I don't know how to call it. So map and the player. So here in the map, the first byte represents the map for boxes. So like that 1 digit in hexadecimal can be represented as 4 digits in binary, which is very handy. So whatever hexadecimal values we have here we have the binary representation. So if we have a look at the hexadecimal ones, they don't make that much sense, right? But if we have a look at the binary, that if you look precisely here, you can see that this is how the boxes are located. So just to give you an idea, just have a look at the boxes. So this is the pattern for boxes, okay? And this is the pattern for boxes here. So this is the pattern for walls, and this is how the walls work. Now let's say this is the patterns for destination squares, and these are the destination squares. 1 box already lands the destination square, and the player, and here is the player. So this is how it works. This is the board representation, okay? And all the logic to get the squares of the walls, to get the boxes, is just a matter of shifting the bits left and right, and then adjusting the counter of the rows. So try to pick up the one of this kind of rows representing at the same time, like if we're dealing with a map, then we just have the boxes and the walls, and this is very handy for collisions when we want to have a collision between the box and the box and box and the wall. So this was one of the savings. So initial version didn't have this. So initially I have walls and destination square and boxes and players. For I thought that would be better, but that actually wasn't so. So because the most bytes consuming code is the collision detection code, where when we need to detect the collision between the boxes and the walls and boxes and other boxes. So I've been rewriting this code at least twice, like completely from scratch. Then I was rewriting this as well, but not that, like not the entire part, but just some core parts, mostly the collision detection in particular. So eventually this code, so I managed to entighten the code from to shave more than 81 bytes. So actually I shaved even more eventually, because 81 bytes was working, but without highlighting the boxes when the box lands the destination square. So that was taking another 9 bytes or so, and then I needed another bytes for initializing the data segment, and for respectively for the GameOS version I needed to jump back to shell, which the far jump takes around 6 bytes, right? EA00, it's 400. Yeah, it takes 8 bytes. Sorry, 8, 1, 2, 3, 4, 1, 2, 3. Yeah, 8 bytes. So far jump, takes 8 bytes. Yeah, so I needed lots of space really, and yeah, let's have a look at this code structurally. Well, for those interested, I've commented every single line of code, and wherever some hacks to shave some bytes are used, this is mentioned, so you just can read through this as if this was a book. So I do this especially like just for those interested how this works, and just a very general understanding. So here we have the boot sector version, right? So the very first thing, we need to initialize the data segment in order to hook the variables like player and the map, where we have the bits representing the walls and boxes and destination squares and the player itself. Here again, like this low and high bytes are in other variables, just for a quick reference for this, in case of the map, this is the low byte. In the low byte we have the walls, and the high byte we have boxes. In the player map, the lower byte is the player, the higher byte is the destination square where the box lands, right? And then the print routine. So print routine is has also been entitled. So eventually print routine takes around like this. Just to give you an idea, so this in the overflow version we had, well, it was slightly bigger. It's already. Sorry guys, it's a new one. It was much bigger in the previous iterations of how the source code looked like. So yeah, it's all about the eventual result. Doesn't matter. No one really cares about this. It's all about the entire gist is within the source code and how actually to make it, right? So printing the map. And now the main loop, what we do here, so we print, so we are printing the row in 2 rounds. So in the first run we print the boxes and the walls, and then we print the player and the destination squares. And this is also involved in the logic of highlighting the destination squares if the box is there, okay? So that also makes sense, okay? And then we're just waiting for a user input, and depending on which of arrow keys has been pressed, we do process them in here in controls part. So it contains, so every direction consists of 2 major parts. So moving the player, which on its own, it contains the collision detection as well. Probably, is this in the cleanups? I was studying this so hard that I don't even remember. So where the collision detection is called? Hold on, guys. Cleanup. Yeah. Yeah. So well, it's probably I need to. I call this cleanup because it clears and sets the player just to perform some routine, some cleanups, implementation dependent cleanups, but also it calls the collision. So every time we say we want to move up or down or left or right, after making this graphics cleanup, the most essential thing we call the collision detection, which allows us to answer a simple question. So whether a player hits a box, okay, or hits a wall, or hits a box. So in case if it hits the wall, I'm using CL as the flag, and if it hits a box, I'm using DL as the flag, and then within the direction. So if we hit a wall, we just go into the opposite side. So we kind of like move there, so 1 step ahead, then collision detection. So if we find ourselves on a wall, then drop back. That's the logic. I was trying to implement the logic of trying to for a loop to oversee like 1 square ahead, 2 squares ahead, but that resulted in absolutely enormous amount of bytes that I was like overflow was absolutely awful, so that didn't really work. And the way how it worked to actually fit this 512 bytes, so first we just we kind of like step into the wall, and then we detect like, are we in the wall? If so, then we just drop back. So this is how it's working. This is one of the core design decisions I came up with intuitively. By the way, this was the very initial decision. Then I started some planning and came up with an even bigger version. Yeah, but then I drop back to this drop back to this intuitive initial version, and this is the best one to from the size of the code perspective, from the number of eventual bytes that we have in the binary executable. So if CL is equal to 1, so if CL flag is true, then we just drop back. And if DL flag is true, this means that we actually hit a box. And when we hit a box, a branching occurs. So we might either try to push the box, or if the box is going to be colliding with another box or with a wall, in that case we need to drop back. So this is done in this box up, box down parts, box left and box right. So let's have a quick look. So I'm just detecting another box, and if I hit another box, then it just dropped the initial position. Okay, and then I'm pushing and popping all the registers to the stack is the matter of preserving the player X offset bit, which we just move back and forth all of the time to like the next move it to the next square bitwise end, then drop back, and again like so we manipulate this bit all the time, but after bitwise end it might get smashed, so we need to restore it in order to save some bytes on reinitializing it from scratch, which is quite pretty. So here it's very expensive using this effective address. It's way more expensive as opposed to just pushing and popping them back to the stack back and forth. Okay, and then we convert CL to CH to CL because so first we've been bitwise ending with the higher bit and to detect the box, and then we need to, in order to detect the wall, we need to shift this nibble to the right. And in that case, because we have the walls in the lower bits, there we can detect the walls, right? So once we've detected the walls, we can answer the question, so do we hit the wall actually? So this end operation. So if we do hit the wall, then we just drop back to the initial position. Otherwise, for all the cases, we just clear the box, adjusting the offset for a box of where to move. So here, if this is the vertical movement, we just adjust the counter of which row we currently are, and then drawing the box is just a matter of ORing back the box. So here we just XOR the box, here we OR the box back. Okay, and this happens exactly for all of the boxes, right? And for horizontal movements, we're not adjusting this row where the player currently is, but instead we just dealing with we just shifting left or right respectively the player bit. Okay, so the new not the player bit, well actually that's already like one step ahead of the player. Okay, so and here is the render dynamic element. So for cleanups, it's very nested. It's really kind of like functions, calling functions, and all serves the only purpose to save the bytes. Okay, yeah, so clearing the player. Yeah, by the way, let's say here is an interesting way to save a few bytes. So when I'm clearing the box, I'm calling the set player, and you might be wondering, why do I need this? So I'm calling the set player just to initialize the BX, the offset, this offset, just to figure out where exactly which row we currently are. So it has some unintended side effects that I needed some more bytes to reduce those effects back, but again, like eventually this allowed to fit this entire thing into 512 bytes. So yeah, and well, this is pretty much all about it, guys. So yeah, now the very last thing, a bit of a bonus. I've prepared some funny sketches for you, just to have a better mood in this not really that great autumn evening. But anyway, so just to make a bit of a fun. So how did I feel while doing this? So without further ado, let's actually go for this. And this is it from my side, guys. So thanks for watching and enjoy the show.